it takes a longer time. But here everything is recorded as video, and the data is already collected. So I'll just walk you through how the data were collected, and after that we'll watch the video, and the last portion will be work with the grounding model using WinIGS. Okay, so that is the plan for today. Now, the ground resistance, which is a very, very important parameters of a grounding system, we can measure using fall of potential method, which was discussed yesterday. All right, so again, one more time, let me explain how fall of potential system method works and how we'll measure the ground resistance. So look at here. So in this figure, so here is our grounding grid. Okay, so grounding grid is here. This one is our grounding grid. Now, by definition, the ground grid resistance is the resistance between any grounding component and the remote earth. And remote earth is by definition is the surrounding this grounding grid, any area where any extra current injection through this ground grid doesn't have any impact. Okay, it doesn't have any impact. So let me show, let me watch a video related to it will explain you the touch and step potential, which you already know. On top of that, I will tell you what is the remote earth. Okay, I'll stop sharing the instruction. Now let me share the video. I think I will have the video here. Yeah, I'll have the video here. So can you see I am on a new window? Yeah, it's YouTube. Can you see it? Daniel is responding yes. So please have a look on this video. Okay. So is the sound okay? Is the sound okay?
You gotta hit play for us to tell.
Can you hear the video, or you can watch it, but you can see it. Can you hear the sound? No sound. Okay, no sound. Let me then stop it and share it again. Share it again. Let me see. Oh, yeah. Yeah. Now, I hope that you will have sound, everything. Okay.
If you contact a power.
So is it okay now? Is the sound there?
Yes.
Yeah, it's all good.
Okay, sound good. Yeah. Please.
Line with your vehicle, call for help, stay where you are, and keep others at least 10 meters away from the vehicle. In the event of a contact, it is not just a vehicle.
So here is a short circuit. See, underground cable. It is in contact with this equipment, and it's short circuit.
Equipment or object that could be energized. Everything within a 10-meter radius of the contact could also be energized.
So what happens is the current is now free to pass through the ground. As a result, see the surrounding the area where the short circuit happens, we're having a voltage a voltage gradient. Okay, so now definitely each circle represent a particular amount of voltage, and voltage in each, this is called equipotential line. This circle is equipotential line. So voltage in each point within this line is the same, but as you move further away, there will be different voltage. So the further you will move from this epicenter, the less voltage gradient you will have. Now, if you move far away, in certain area, you will find where there is no any voltage. Okay, so that the area is called the remote earth. Okay, now the ground resistance means if here instead here was a grounding grid and the short circuit happened right, short circuit current is injected right into the ground grid, then definitely our object is ground grid, and because of that current flow through the ground grid, definitely surrounding this area will be under the influence of voltage gradient. But if you move far away, there will you will find some area, okay, surrounding this grounding grid where there is no any impact because it is further away. So resistance between our grounding object within our grounding grid and the remote earth is the ground resistance. Okay, now anyways, watch this video that it will tell you something about the touch and step potential.
That's why you have to be aware of both step and touch potential. With step potential, electricity spreads, like ripples or rings, over the surface of the ground, away from the point of contact. Each ring carries a different voltage. If you step into one ring while your foot is in another, the electricity will make up the difference in voltage through your body.
Yeah, so that's what will happen. Now, if this person stand on this circle, okay, both leg on this circle, one leg, let's say here, another leg is far away, but within this circle, then there will be a current flow through his body. Why? Because there is no any voltage difference. But if this is the way he will move, definitely his 2 feet will be on a different voltage level. So that voltage difference will cause a current flow through his body. Okay.
With touch potential, if someone on the ground touches what is in contact with the power line, electricity will travel through that person's body to get to the ground. If you hit a power line, you can try to break the vehicle free of the contact, but only if it doesn't cause more risk to yourself or others, or more serious damage to the power line. If you can safely brake from the contact, move the vehicle or equipment at least 10 meters away to safety. If you must exit the vehicle, only in the case of a fire, jump away from the equipment with 2 feet together, then bunny hop or shuffle at least 10 meters away from the equipment. Don't take large steps, as there is the potential for electrical current traveling through your body. If you're not sure you're far enough away, slowly move your feet apart. If you feel a tingling sensation in your legs, you are still within the step potential zone and must continue to bunny hop or shuffle away.
Okay, so here is the video. Okay, now let me close it and start out. What?
Tape and prep to protect your home. Step 1.
No. Okay. Let me share share again our lab instruction. Here it is. Yeah, here we are. So definitely because of fault current through this grounding grid, surrounding area will be under the influence of voltage. Okay, and that voltage basically ground potential rise. Okay, now in this lab we have to inject current instead of right into the grounding grid, we'll inject current far away any point using the auxiliary electrode. Okay, so the distance from this grounding grid to that auxiliary electrode, according to the IEEE standard, is minimum 6.5 times of the diagonal distance of this grounding grid. Okay, but if you go a little bit further, it doesn't bothers. Okay, so what is done here is, so let's say this is grounding grid, where definitely we have transformer neutral is connected to the ground. So that transformer neutral is our reference. Okay, and we will drive the auxiliary electrode far away from the ground grid, any direction which is doable for you. um, so here is the auxiliary electrode we are driving into the soil, and we are, and this auxiliary electrode is connected to this reference point. Okay, and we're injecting current through this electrode, and current definitely will go back to its source through the soil, and will be collected by this grounding grid, and this grounding grid will provide this current to this neutral of our transformer. So now here we'll have grounding gradient, and here also we'll have grounding gradient. Now, as this point is far away from this grounding grid, in between them, there will be some area which will be possibly beyond the influence of this potential rise. Okay. Now, uh, this distance will keep constant. It means once we'll drive this auxiliary electrode, we'll keep it here, and we'll inject the current, and current definitely will be flowing through this loop, and our earth or ground is also a part of this loop. Now we'll take another electrode, okay, electrode Y, and we will drive this electrode Y starting from closer distance of this reference point, and we move further, and for each position of this Y, we'll measure the voltage, and we'll see that when this Y is very close to this X, okay, reference point, then the voltage will be not that big, small amount. Now further we'll move, voltage difference between this reference point and this auxiliary electrode Y will be higher, and at certain point we'll see that voltage is not changing. Why it won't change? Because at that area we are not having any voltage. Voltage is equal to 0. Okay, so if here voltage is 0 and there is voltage is 0, then the difference from this reference point to this 0 voltage point will be the same. So voltage will be the same. And now if the voltage what we'll have for different position of this electrode will divide by this current, then that will be resistance. Basically we'll collect all those resistance data, and we'll move further with our auxiliary Y leads, and at that point our Y lead will come under the influence of the voltage gradient due to the current through this auxiliary conductor or auxiliary leads Z. Okay, so at that point we'll have different voltage. Okay, and if we'll come very close to this Z, then our voltage will be even higher, and the same way we will calculate the resistance. And with respect to the distance from this reference point to this auxiliary electrode through which we are injecting current, and the resistance between these, that will be the characteristics. So in between of this reference point and the auxiliary electrode through which we are injecting current, will have some area where our resistance will have the flat portion. So this flat portion means here is our remote earth. basically. And by definition, ground resistance is the resistance between the ground grid and the remote earth. Okay, so the resistance we'll find here, that resistance is basically our ground grid resistance. This is the theory behind the measurement of ground grid resistance. Now, experimentally, it was proven that the distance from the reference point to the remote earth is basically 62% of the total distance of this reference point and the auxiliary electrode through which we are injecting current. Okay, it means if the distance of our auxiliary electrode Z through which we are injecting current and our reference point is equal to A, then 0.62 times A, that distance from the reference point will be the distance where the measurement resistance will be basically the ground resistance. Makes sense? Did I explain it nicely, or you have any question? So 62% of the total distance from X to Z. Okay, between them the distance, and if we'll put our auxiliary electrode Y, which we are using in order to measure the voltage, at 62% of this total distance, and by measuring the voltage and calculating the resistance, we'll get the resistance which will be basically the resistance of our grounding grid. Okay, does that make sense? Any question? So do you have any question, anyone? Okay, if you're clear about that, then that's fine. Now the thing is, using the AEMC 6472 ground measurement equipment, we perform this measurement. Okay, ground grid resistance measurement, and there a chart box you can see. So in a weird way, if both your feet are in electrified water, it is safe at neither. So this is an interesting question. That question. So that Christopher is asking. Yeah, the main thing is we are in danger if the 2 point will have different voltage. Okay, so if your both feet is in water and water is having the same voltage, then you are safe. See, the person is sitting on the car. This car is under voltage, but this person is safe because every metallic part of this car will have, or truck will have, the same voltage. All right, so yeah, you are right. If you can provide, even the show insulation doesn't stop the flow of current. Yeah, it does, but there is no any guarantee, because the manufacturer make shoes, they don't follow any criteria in terms of the resistance of the sole. Okay, so when we design a grounding grid, we ignore the resistance provided by the shoe sole. Okay, all right, so yeah, so let us have a look on ground grid resistance, how it was collected, how it was measured. Yeah, Christopher, so you are You are seeing the lab instruction, that's fine. The car I am mentioning is the, or truck I am mentioning is with the video, okay, with the video. So that I am not sharing that one anymore. So I am referring that truck. Okay, so using the equipment, we have to, for this ground grid resistance measurement, we have to put a rotary knob on this position, 3-pole resistance sign, you will see that position, and the distance, which is 6.5 times of the diagonal distance of the grounding grid. We are putting an auxiliary electrode, and that electrode should be connected to this terminal, H terminal. Okay, and this E earth terminal will be connected to the object. What is our object? Object is our grounding grid. Grounding grid, we not necessarily to dig the soil and connect to the ground conductor. We can connect to any equipment riser which is connected to the grounding grid. So most of the time we use the neutral of the transformer, which is definitely connected to the grounding grid. Okay, so that's where we'll connect this one, and the other auxiliary electrode, which we will move from this reference point toward the direction of the auxiliary current, auxiliary electrode through which we will be injecting the current. Okay, so and this auxiliary electrode will be connected with this S terminal. Okay, and definitely we have to set up this distance, so main distance, which is A. For our lab purposes we are using 50 meters. Okay, and yeah, the distance we are using here is the main distance 50 meters, and the Y auxiliary electrode we are placing in different distance from the reference. First distance is 5 meter, then 10, 15, 20, 25, 30, 35, 40, 45, and 50 meters. Okay, and we are definitely, first of all, this A distance we are keeping constant. Okay, here you can see A distance. Second button and distance button, A distance will put here 50. We'll keep it constant. And after that, whenever we'll change the position of the Y lead, while it is this one, okay, we definitely have to change it in here as well. Okay, 5 meters, 10 meters, 50 meters. Each time we will physically change the distance of this Y lead, we have to change here the value of D as well. Okay, and then we have to press the start button, and the meter will give the data, and that data is collected here. Okay, now please pay attention here. The resistance we got for different distance here, 5, 10, 15, 20, 25, 30, 35, 40, 45. So 63.6, 63.9, 64. So different resistance we are getting. Okay, so difference value we are getting depending on the distance of this Y lead from this reference point. All right, now using this data table and having 9 different resistance values, what will be your ground grid resistance? Okay, you cannot use all of them. So now my question is, please step forward and answer my question. What will be your ground resistance from this table? Look at this table and tell me. Anyone? Will it be 63.6 or 64.3 or some other number, 63.9 or? So I discussed you what the ground resistance is. Is it just the average? Eric is answering. I'll tell you, no, it is not the average. So just try to remember what I just discussed you, what the ground gate resistance is. And according to IEEE standard, usually at which distance you should put the so Kaveh is answering 63.8. Why Kaveh? It is 63.8. So I will tell you the answer. It seems me that if it seems to me that you didn't listen to me carefully, or I was not able to explain you very nicely. That's the flat portion of the curve, right? Flat portion of the curve, yeah, but that flat portion could continue several meters. They are also within this. Yeah, that's right. Yeah, but the easiest way to find this ground resistance, definitely that you're right, Christopher. You're right. Yeah, that's right. But look at our table, and from here, please tell me what is the distance of the auxiliary electrode through which we are injecting current here. Distance of the auxiliary electrode from the grounding object or grounding gate, okay, and through which we are injecting current. That distance is 50 meters, right? 50 meters. Look at here. So this is our grounding grid. From here, the distance of Z electrode, and Z electrode is our auxiliary electrode through which we are injecting current. So this distance is A, is equal to, in our lab, 50 meters. And I told you that usually, definitely we'll have a flat area, and that flat area will start when you will move with your Y electrode from your reference point about 62% of this total area. Does that make sense? 62% of this total area. So our total area in our lab is 50 meters. Okay. If you will move from this reference point, 62% of this total area, that distance is 31 meter. From here to there, 31 meters. Now see that table, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So the flat area will start somewhere from here to there, somewhere, okay, from here to there. Because 62% is 31 meter, but we didn't take any reading for 31 meter. Now you could you could look at these two number for 30 meters, which is 62.6 ohms, and 35 meters, 62.4. So your ground grid resistance will be somewhere between here. Okay, and remember, this is a part of your final report. I noticed that because of you don't pay attention, you just put any number from here as ground grid resistance. That doesn't comply with the theory and with the data. So definitely your ground grid resistance for this data will be close to 62.6. 62.6, and between 62.6 and 62.4. If you take the average of these two, that will be fine. Okay, I'll consider that. Yeah. So resistance for a distance of 31 meter, we don't have 31 meter, so you can take average of these two value, and that could be considered as RG. Okay, and if you won't do that, you will put some other number. It means you don't understand what the ground grid resistance is and you are not able to measure it. Okay, so for that answer, you won't, for this portion you won't get any mark. You have to be very clear about where the ground grid resistance you have to measure. Okay, makes sense. Okay, so that's how you'll define. Now see here we are moving from this reference point. So this is the grounding grid. Okay, we are moving toward the auxiliary electrode through which we are injecting current. Now my question is, if instead we'll move on opposite direction this way with my Y lead, or this way into the page or out of the page. Okay, let's say this is east direction, this is west direction, this is north, and this is south. Now in between the grounding grid and this auxiliary electrode through which we are injecting current, we are using our voltage measuring electrode. So we are moving from reference point to west. Now my question is, no, I don't want to go to west. I want to go to east from this reference point, or I want to go to north or south, or in between north and south, or north, whatever direction I want to go. So my question now, will that be appropriate for me to get the ground grid resistance? Please think of it and answer. Anyone? No answer? So again, okay, I don't think you could do that. Okay, Eric is answering. Then yes, Kabe. Yes. Yeah. Kabe, why yes? Let's say I'll go to northeast from this reference point. According to your answer, you know, I understand that you agree with that. So how it is okay? And why? Okay, Eric and Kaveh, see, and everyone, please listen to me carefully again. So according to the definition of our grounding grid resistance, the grounding grid resistance is the resistance between the grounding grid and the remote earth. And the definition of remote earth is the area surrounding this grounding grid where you are not having any influence of this current flow through the ground. And that area not necessarily will be in between this electrode and that reference point. It could be to north, it could be your to your east or south. So because of current flow, incoming current or outgoing current, by the way, this current is AC, so they will flow this way and that way. So you will have a voltage gradient surrounding this area. So you have to find a point from this reference object where there is no any voltage. It means that point is beyond the influence of this potential rise. So that point could be in north side and east side, south side, and at this side and that side, everywhere that point you can find. So as a result, not necessarily you have to move with this voltage measurement electrode Y toward the current injecting auxiliary electrode. You could go in any direction. Main thing, you have to find the flat area. Okay, you have to find this flat area here. Flat area means if you will collect the resistance. Where is that? Oh, here. Yeah, so you have to reach to that region where your uh, curve will have a flat portion. Okay, now definitely if you won't move toward the auxiliary electrode through which you are injecting current, you won't get this one, because this one will have when you are coming under the influence of this. But that's not important. Important is to find out this portion. Okay. Okay, so does that make sense? So theoretically and practically, you can move to any direction in order to find out this area. You will find this area. Doesn't matter. You will move toward the current injecting electrode or into opposite direction from the reference point. All right. So yeah.
Yes, Nurul. Okay, sorry I couldn't answer because I went to connect my microphone, but then I shut down the computer. So
Okay,
I got
Kaveh, that's fine.
disconnected. Sorry for that.
No,
Yeah.
it's okay. Yeah, thank you very much for stepping forward, and
Welcome.
Eric also. Yeah. So yeah, this is the way you have to interpret how we can use this follow potential method to find out the ground gate resistance. Yeah, absolutely. Yeah. Chris, you're right. Yeah, regardless of the direction, you have to find the remote earth. Basically, remote earth you could find in at any direction. Okay, so the data is here. Using this data, you will prepare your final report and make sure the thing I just explained here from this column, which number is your ground resistance, you have to figure it out. Okay. All right, so this is the first part of this lab, and the second part is touch potential. And you know the definition of touch potential. Touch potential is basically the potential of any ground point 1 meter away from the grounded object. So in the video which we watched together, grounded the object was the metallic part of the truck. Okay, so from that truck 1 meter away, if you measure the potential difference on voltage difference, that is basically the touch potential. And step potential is definitely the potential between 2 points apart, 1 meter apart from each other, and not necessarily that 2 point could be very close to the faulted object. It could be anywhere away, but usually within 10 meters of the faulted object, because beyond 10 meter you will have less voltage, so you may have some error. And basically the step potential we measure not very far from the substation fans or any equipment. Okay, so whenever any fault may happen, so if you will be close by to the grounded object, then we have to provide the safety, and that's why we have to measure the step potential as well. And step potential definitely potential between your 2 feet, and according to the standard, the distance of 2 point, as if you are standing putting your foot 1 meter away from each other. Okay, and standing, putting your foot differently, 1 meter apart from each other, within the same area, you could have different step potential. And it is because if both of your foot will be on the equipotential line, okay, equipotential line, then you won't have any step potential. But if you'll stand putting your feet in between two equipotential line, definitely then you will have some step potential, and because of that step potential, you will have current flow through your body. Okay, and in touch potential, definitely you have to set up the equipment this way. So all 4 terminal you are using, but this bottom 2 you have to jumper together, and these 2 must be connected to the grade. Okay, grade reference point. Okay, and this auxiliary electrode, definitely you have to inject current, and this will act as the fault current or short circuit current. Okay, and this Y lead you will use in order to measure the touch potential, and definitely you have to drive this Y lead only 1 meter away from this ground object. Okay, if you have a substation surrounded by fence, then 1 meter away from the fence you have to place this electrode and measure the voltage between this electrode and your substation's grounding object. Okay, you could move surrounding the substations, and in different location you will measure the touch potential, and you have to make sure that the measured touch potential must be below the allowable touch potential. Okay, that things is the purpose of this analysis. Okay, now step potential, again you will inject current. Okay, far away, so same distance you can use the distance we used here for our ground potential ground gate resistance measurement. Okay, now for step potential, again we'll have all 4 terminals, but only the grounded object will be connected to the bottom terminal E, and 2 auxiliary electrode will connect to S terminal and ES terminal, and that 2 electrodes will act as our foot. Okay, when in any areas we'll put that 2 electrode. Here you can see these 2 electrode 1 meter apart from each other, and we'll measure the voltage, and voltage difference between these 2 electrode is basically the step voltage or step potential. Okay, so the way it is done, so this is the way we have to wire up our meter and connect to the electrode. And here and in previous one, we don't have to set up any distance from this and that, because this 1 meter, it automatically will consider that 1 meter. But this distance we could include. So everything is discussed here very nicely, but the bad thing is that you are not doing this experiment by yourself in person. It could be very interesting, and you could collect those data by yourself and be excited finding those data. Okay, now the objective of this course is this is the way you are collecting the data. And for step potential, by the way, here is the data which was collected. Now using the soil resistivity of the same area, you are modeling your grounding grid using WinIGS. Okay, so you will model it, and from your model running the software, you will find out the ground grade resistance. Okay, here in lab you are measuring ground gate resistance and modeling your grounding grade. You will calculate ground gate resistance. So in real life situation, when you will take the measurement in a close by an existing electrical substation or station, and all the measurement will do in your site, and whatever information you could have from your system, you will put in the WinIGS, and you model your grounding grid. Okay, and using the your model in the same area, you will take the measurement of grounding grid resistance and touch potential and step potential. The two results, measuring result and calculating result using WinIGS, will be very, very close to each other. Sometimes it will be the same, or if not the same, very, very close to each other. Okay, and you can verify them if you will have any opportunity to do that. Now in here, in our course activities, we are not going to the real site. We don't have any real grounding grid installed. Okay, so soil resistivity data we are giving definitely to our model, WinIGS model, but the conductor you are using in your model, the fence you are using, ground rod you are using, all those things, ground grid component, we don't have. But still, we are pretending as if we have it. And in the video, I am trying to show you that this is the way we have to measure the touch potential and step potential and ground grid resistance. Okay, so that value will differ from the value you will find using WinIGS model. Okay, and the difference very obvious. Okay, so but in your report you have to include this measuring measuring data and your calculating data by using WinIGS, and in each step you will put 2-3 lines conclusion in each step, and at the end of the report, you will put a final conclusion, and in there you will explain uh, you know main thing is you will explain about the safety, the model you designed, is it safe, that things you have to uh, put down in your report, and the comparison of your model data and the measuring data, and this comparison you will see that there is a huge difference, and why is that difference is there also you have to explain. Okay, so as I asked you to prepare the report as if you are doing a real work, so that the way you will start and complete it, but at the end when you will put the final conclusion, then you will reveal the truth. The truth is uh, the uh, the data you will get using WinIGS model and the data which we are collecting are very, very different, and the reason of difference is this and that. You will include that at the final conclusion. Okay, so that's what you'll do. So yeah, that's all for the data collection of our lab number 3. Okay, if you have any question related to this lab, please go ahead and ask me. I will be happy to discuss about that and explain you if you have any question. Anyone, any question? Okay, now that's good that you you got the point. Now let me check the attendance, because I am having, how many students I am having? I am having 12 students. I think everyone is there. So anyways, as usual practice, you will so here is the, yeah, you will type yes on your chat box. Okay, I know you are there, but still you just type. Don't ignore it. Just type yes. Kaveh, are you there? Yes, good. Now Daniel, good. Paul, I think he was absent. Paul is not there. I think Paul. Anyways, Paul, are you there? Paul, yeah. Christopher, I will talk to you. Let me finish the attendance, and I'll answer your question. Hanley, are you there? Hanley is there. John Esterbrook is there. Jayden, yeah. So Rupinder, are you there? Rupinder is there. Eric is there, and Ilya Maslov. Oh yeah, Ilya is there. Rachel is there. Christopher is there, I know. Yeah. Ranveer is there. Jared is there, and Joshua. Okay, fine, wonderful, very good. Now let me go back to Chris' question. If it turns out we made an unsafe setup, would that be an appropriate report to the submitter? So unsafe setup in terms of collected data in the site, I mean measurement data could be unsafe, that's fine. But your WinIGS, in your WinIGS modeling, the data you will get, that data must be within the safe range. Okay, that's for sure. Now, when you are modeling at the beginning, when you analyze it, you may not have the safe data. Then you have to, modify your model. And how you'll modify, I will definitely discuss you. But you have to make sure that your WinIGS model is a safe model. That you have to make sure, okay? All right. Any other question? Yeah. Oh, okay. So now let us have a look, or let us watch the video. Okay, first we'll watch the video, and then we'll start our modeling. All right. So let me open the video now. Okay, so let me share the video. Video is not there for something. The video is not there. Okay. Okay, I'm starting the video. Please let me know if there is any problem. Definitely the quality of video is as usual is not that good, but still, yeah, just have a look.
Now we're gonna start our third and last lab. This lab is about measuring the grade resistance, touch potential and step potential together. So grade resistance, we will measure using the method called fall-off potential. In this method, we have to select a point, grounding point within the substations. Unfortunately, we are not in a substation now, but we will pretend that this tennis court is a substation. So surrounding this court, there is metallic fans. The same fans we will have in our real electrical substations. But the difference between that fence and this fence is that fence, what is surrounding the substations perimeters, is connected to the ground grid. They have underneath ground grid. We don't have ground grid here underneath. Okay, so the reading will have it is you understand that it's not real reading, but our objective is to show you how to measure that value. Okay, whatever value you will get, that's not important. The important thing is how select a reference point in the substations. What is grounding point? It is usually it is the grounding point of the transformer. So from there we'll go any suitable distance, and that distance should be 5 to 6 times the perimeter of the substations. Okay, that distance will go, we'll find the grounding object there, or we'll put our probe there. Okay, and we'll insert current through that probe, and that current will pass this distance and come back to the ground grid of these substations. Okay, now along this distance, in each 5 meter we'll measure the voltage. Remember, we are inserting current in a far away distance, what is equal to 5 to 6 times the perimeters of the substations. Okay, and from that grounding reference point we'll move toward that current injecting point, and each 5 meter we'll measure the voltage. So it is set up the distance from the grounding reference point to our probe is 50 meters, we are assuming, and we are using 50 meters, and this is our grounding reference point. From here we'll use another probe, and each 5 meters will move from here, and we'll measure this meter will measure the voltage. Okay, so the setup is ready to go. We have first 5 meters, and we'll take a reading, and then we'll go 5 meters more, 10 meters from here, and then 15, then 20, 25, 30, 35, 40, 45, and 50. So this is the way we'll take the measure, and meter will give us the resistances. That resistance will represent the ground resistance. Now the thing is, this resistance will be different in different point, but we'll see that somewhere there's difference will be the resistance will be almost the same. In 2-3 readings will be almost the same. So as a result, if you draw a curve of the resistance with respect to the distance, we'll see the curve will be flattened in some point, like a plateau, and that value of resistance is representative the ground resistance of this grounding system. Okay, and theoretically that distance should be 62% of the distance of the probe from this grounding reference point, by 62%. So if our distance is 50 meters, then that the location what will give us the ground resistance will be around 31 meters. Okay, because for 100 meters it will be 62 meters. We are using 50 meters, so it will be 31 meters. That's what will be. Okay, that's the theory. Okay, now let us take the reading, first reading for 5 meters. Okay. According to the fall-off potential method, we set up our probe. Now we have to set up the mirror itself. Now this H is connected to the probe what is 50 meters away from here, and this S is connected to the probe what will be moving. This 50 meters is constant, we won't change that one, but for S that probe will change the distance from here, first 5 meters and then 10 meters and 15 meters, and this one, this earth one, is connected to the ground gate itself. William, can you show the where it is connected? That way. Okay, now the conductor is connected and probes are set up. Now we'll set up the meter itself. So for this follow potential method is 3-pole method. We'll put it in 3-pole location here. Now distance we have to put. So first distance D is 5 meters. So second and distance we are placing it into 5 meters and increasing. So 5 meters is set up. 5 meters is set up. Now we have to set up the distance A. So distance A, again we have to put this second and distance, and we'll go this way, this way, this way, this way, and we'll go back here. Here we are in A. So A is our 50 meters. So see, blinking will increase the distance, this 10 meters, 20, 30, 40, 50 meters, and second and distance again. Okay, so this A represent the distance of the probe through which we will inject the current. That will be fixed there, we won't change it, but this D will change. Okay, each time we'll take reading and 5 meters will go away that way. So everything is set up. Now we can start the start button. Press the start button and we'll have some reading. Yeah, we got the resistance here equal to 63.6 ohm. 63.6 ohm. Okay, and the distance is 50. A is 50, D is 5. Now we'll have a look the voltage. What the voltage we have? Voltage SES is 482 millivolt. Okay, and current is 7.58 milliampere. So we have our first set of data. Okay, now what we'll do is we'll change this distance D, okay, using that the probe. We'll move it 5 meter away from the position at it now, and then we'll change the distance here. Physical distance will change, and in meter also will change the distance, and we'll take the reading again. Okay, so let's see how we'll do that. So here we have 5 meters. We have to go now 10 meters from the ground gate. William, can you? Okay, you can record. So we have changed the physical distance of the probe from the grounding reference point. Now we'll change the distance here, D. So second distance, so instead of 5 we have to make it 10. So 10 we will make it we have to make it 10. We can go up, 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 up. So here we have to put 10. We have 10 second and distance again. So it is set up. So our main distance for current inserting is 50 meters is remaining the same, but D will get changed to 10 meters, and we physically also put the probe 10 meters away from this ground reference point. Now we'll take the measurement. We'll press the start button. So the reading of resistance is now 63.9, 63.9, not that much, and the other values are, voltage is 484 millivolt and current is 7.59 milliamperes. Alright, so we have data. Now we can change the D to next level. What will be 15 meters? We can do right now here, and then we will change the physical distance. So second and distance, and here in 0 we have to put 5. So we have D is equal to 15. Now we'll place the probe 15 meters away from the grounding reference point. We set up the distance of the probe equal to 15 meters, and we'll press the start button. So the resistance is 64.5 ohms, okay, and the voltage is 489 and millivolt, and current is 7.59 milliamperes. So this is for 15 meters, and now 20, 25, 30, 35, 40, 45 we will take the measurement without recording, and the last last reading we'll record again. All right, okay, let's go. Tab number 3 is the touch potential measurement, and it is done by assuming that somewhere close by, inside or outside of the substation, a fault happens, a short circuit happened. Okay, so definitely current will pass through that short circuit point to the ground, and it will have impact on overall grounding system, and whatever normally known current carrying enclosure or fence, whatever, all of those things will be under voltage impact, and if you touch that, then because of that voltage, current will pass through your body. So now we will assume that short circuit happens somewhere close by, and there we'll put this probe, and we'll use our meter, and we'll discuss how we have to measure the touch potential. We'll measure the touch potential from the grounding grid or whatever connected to the ground grid 1 meter away from there. So 1 meter represent one step. It is definitely a little bit higher than one step, but that's the standard we use. Okay. All right. Measurement, we set up our we connected our probe with the meter, and we'll set up Meter setting by using the rotatory knob here. You have to put it in 4-pole position here. 4-pole position. Okay, we did that, and now our SY, this one, this is set up 1 meter away from the grounding grid. This part, as if it is a part of the grounding grid. So 1 meter away. Now we'll press the start button, and the grounding measuring meter will start to measure. So the resistance it is giving is equal to 33.97 ohm. So 33.97 ohm. Okay, and the current what is get injected we'll find from here. Yeah, here's the current we have. Current is 16.7 milliamperes. Okay, so from this reading we can get that if the short circuit current will be equal.
Okay, so at this point, I want to emphasize one thing, which is very important. So in first reading, you can see that the current is some milliamperes, and the resistance is 33.97 ohms. And touch voltage also it will give, you know, I don't know how much it is. Let me, yeah. So touch voltage it will give, which is yeah, touch voltage it will give, which is not that high. Now the amount of current, which is several milliamperes here, which is that current basically? Let me run it again. The amount of current.
Yeah, here's the current we have. Current is 16.7.
Okay, so current amount is 16.7 milliamperes. Okay, milliamperes, and the resistance is 33.97 ohms. So the touch voltage will be around you know, so 16 point some milliamperes and 33.9, it will be very negligible amount. Okay, it will be less than a volt. Okay, half a volt. So that half a volt is the touch voltage. Now my question is, this 16.7 milliamperes of current, what is this current? What is that current? That current is the current which is getting injected. Yeah, that's right. That's right. Now, in your case, how you define the touch voltage? So 16.7 milliamperes times 33.97, it will give you 0.567 volt as charge voltage. Okay, let's say this is part of your grounding grid, whichever you are designing, and at that particular point you are calculating the touch voltage from your model, grounding model. So if you want to relate this real data with your grounding model, then how you will find out this touch voltage? Touch voltage here is 0.567 volt, 0.57. Okay, less than 1 volt. How much voltage you will have? So definitely, maybe I am not asking the nicely. It is maybe complicated for you to understand. So, anyways, so let's say your short circuit current is definitely not 16.7 milliamperes. It is different value. What the short circuit value we are using for your model? Do you remember how much short circuit current we are considering? Everyone is having the same amount of short circuit current. Can anyone? 5K, yes, 5K. That's right, Daniel, thank you very much. Now, see, in our measurement, our meter is using 16.7 milliamperes. The resistance is 33.97. As a result, the touch voltage here is 0.567 volt, but instead 16.7 milliamperes. If there was a real short circuit, real fault, and the fault current was 5 kiloamperes, then what will happen? What will be the amount of touch voltage? So definitely you have to scale up your touch voltage. That touch voltage will be the product of this resistance 33.97 times 5 kiloamperes. It will be very, very high, very, very high, much more higher than the allowable touch voltage. Okay, allowable touch voltage you will have in your model. And the reason is very obvious, because we don't have any grounding grid here. As a result, see the resistance in real grounding system, the ground this kind of resistance will be less than 1 ohm. Okay, less than 1 ohm, and at that condition you will have different touch voltage, much more less touch voltage. And when your model will be complete and you will calculate the touch voltage using your model, you will see the touch voltage will be much more less than the one you will have here. But anyways, the data which is provided with this lab instruction, there is a column which is kept empty. Okay, and that empty column you have to put the scale up touch voltage. Okay, scale up touch voltage. That's what I wanted to emphasize here, because it is discussed in lab instruction, although, but just it will be helpful for you. All right, so please be mindful about that. The same thing will happen with step voltage also. You have to scale up. Okay, let us move forward and watch the remaining part of the video.
16.7 milliamperes. Okay, so from this reading we can get that if the short circuit current will be equal to 16.7 milliampere, then the resistance between the grounding grid and this probe is 33.97 ohm. So touch potential will be equal to this resistance times the short circuit current. But in reality, short circuit current is not that much and voltage is not that much, different things. So here in here we have to put the amount of current what represent the real short circuit current, and with that current we have to multiply this value, that will be our touch potential. Okay, this is the just resistance. We have to use this short circuit current and multiply, that will give us the touch potential. So this one reading, and this way we will take some other readings in other in other locations. So we'll just pull this probe up, and again in another location 1 meter away. So second touch potential measuring point is there. Again it is 1 meter away from the fence. We'll press the start button, and basically we need to find out the resistance. So resistance there is 39.28 ohms. Again, the short circuit current, anticipated amount of short circuit current we will put here and multiply that current value, this resistance value, that will be our touch potential. So this is the second point. We'll take a couple of more points. This is basically 1 meter away from this grounding grid. Yeah, here the resistance is 33.37. Okay, we'll take more data, but we are not going to record it. We will take it the same way, but we'll collect those data and put it down in this table. All right. So we collected all the data in 3 different points as our touch potential, and here's the table. It is set it up already. So this part is done, touch potential is done. Now the next part and the last part is step potential. So we'll set up our meter and all those probe all together, and I'll discuss how we will be collecting data, and we'll show the data what will be collected. Okay. For touch potential, this middle 2 probe, we have to keep 1 meter away from each other. These 2 probe will represent 2 legs. Okay, so that's what we'll be doing. In the previous one, this ES was connected with this ground together, it was jumper together, but now we have to use these 2 probe in order to measure the resistance distance between 2 legs representing these 2 probes. Okay, so they're set up 1 meter away from each other. There is 1 probe and there is 1 probe. Now our meter also set up. We'll just press the start button and we'll see what will be the resistance here. Okay. Yeah, so the resistance here is 3.615 ohms, and short circuit current, again it will depend on the real amount of short circuit current, and step potential will be the product of this resistance and the short circuit current. Okay, we will take several more data. So first of all, we'll move this one 1 meter away from our previous probe. It is exactly the same because I measured my step. This 1 meter. So this 1 meter, the distance between these two probes, and we'll press the start button and we'll see what will be the resistance between these two probes. So this resistance is 21.12 ohms. Okay, so the same way we will collect some other data for the step potential, and yeah, that will be the final table of data for lab number 3. And yeah, definitely I will provide you with all those data what we are collecting here with William, and you will have to prepare your report, and how you will do that I will discuss in our lecture class. Okay, so for now we are almost done. We'll take some other data and prepare the table. So we collected the data as our touch potential resistance here only. Main real potential we'll get when we'll multiply these values with the short circuit current, and that current is given by the utility company because they have the model. They know if short circuit will happen in different position, different location within the substation, or outside of substation, or inside the substation, and yeah, you can get that value from here. Okay, so this is all about the last lab number 3. Okay, now you already saw which equipment we used. We have this you know AMC grounding measurement meter, and all those probe and conductors, and these rods, all those things, and definitely we need to use this tape in order to measure the distance from probe to probe, all those things. Okay, and yeah, so that's all in terms of collecting the data. Now all this data you have to put in the model what will be creating by using WinIGS software, and definitely you have to verify and validate your dash potential, step potential, and ground potential rise, all those things. So I'll discuss in our lecture class everything related to these labs, and basically related to the grounding and bonding codes all together. And yeah, I'll talk to you on April the 28th.
Yeah, okay, so this was the this was the lab related to the ground potential, ground grade resistance measurement, touch potential, and step potential measurement. If you have any question related to the way the data were collected, I can go through that. If not, then we can start the modeling of WinIGS software. Any question? Okay, good. Now please open your WinIGS model. I will open mine. I'll open mine, and let us start from there. So, WinIGS model. Okay. Okay, so do you have any technical problem related to the software? Anyone? So software works fancy for. Okay, sounds good. So now we will start this one. I'll close this one. And open another. Yeah. So as of our discussion in last lab class, I asked you to complete your grounding system by installing the ground conductor, fans, and ground rod you installed already, because it didn't take that long, but install grounding conductor was a bit time consuming. Then you have to make sure that the distance is 10 meters from conductor to conductor. So that things was your homework. You should have done that. Okay, so when your grounding grid is complete, you should have copied your grounding grid and paste 3 more times. So in each grounding grid, you should have used the soil resistivity data from 3 different traverses. So north, south, east, west, and northeast, southwest. And these 3 different soil resistivity data would have given you, each of them would have given you a 2-layer soil model, and you should have saved 2 figures for each traverse data, soil resistivity data, right? And in this figure, the information about the soil resistivity, top layer and bottom layer soil resistivity, and the top layer height is given. So everyone should have those data so far. Now my question is, does everyone have those information? And those information is related to your particular grounding model. Okay, so do you have those information already? Kaveh, do you have it? And how about Daniel? Daniel, do you have the 3 different 2-layer soil model? Okay. Hanley, do you have your? Okay. How about John Estabrook? And Rupinder, you already responded as yes. Eric has it, and Ilya has it, and Risha, and Christopher. Christopher, do you have 3 different models? Okay. Ranveer, do you have it? Yes, good. Jared. Okay, wonderful. Joshua. Oh, wonderful. Okay, now what we have to do is we have to mix up those 3 different soil model. How we'll do that? So each model has its own top layer resistivity, bottom layer resistivity, and height. So you will take the average value of top soil resistivity, okay, bottom layer soil resistivity, and the height. So make it average and find a number for top layer resistivity, bottom layer resistivity, and height. Okay, do it now, please. So that model data will be your data for final model. Okay, so does everyone okay, Ranbir, yeah, I am repeating. So you have a soil model for north south traverse data, okay, and for this data you have top layer soil model, soil resistivity, and bottom layer and height. And the same thing you have for east west, and the same thing you have for northeast southwest. Same thing, I mean top layer soil resistivity, bottom layer soil resistivity, and height. Definitely those numbers are different, but for each soil model you have 3 data. One is top layer soil resistivity, one is bottom layer soil resistivity, and one is height. Now all the top layer soil resistivity for 3 models you add up together and divide by 3. Same thing you have to do with the bottom layer soil resistivity. You add 3 numbers from 3 different models and divide by 3, and the height also. That will be the average value. Yeah, tolerance. Yeah. That's a good question, Eric. Yeah, you have to average the tolerance as well, because that's the number within which you can change your soil resistivity and the height. And maybe you have to change it. We'll see. If you have to change it, you will do that. But for now, just take the average. Tolerance also. Yeah. That's a good point. So when you are done, just let me know. And I don't think that it will take longer time, because if you have all the information, you just add them up together and divide by 3.
Nuro, where are we finding these numbers?
These numbers you will find. Do you have 3 different models for 3 different traverses?
Yeah, and I can see the dynamic model fit report, but I'm not sure where to get the final numbers.
So I remember I asked you to save. So yeah, so you remember I asked you to save this model information. So for 3 different model, you should have 3 different figure. I asked you to save 2 figures from each model. One with this data, one is related to this top and bottom layer soil resistivity. You remember I told you that? And I asked that, just right, I asked this question and everyone was answering yes. Do you have this? Whoever have it, see here, upper soil resistivity, this one for 1 model, this one for 2nd model, this one for 3rd model, add up together and divide by 3. With tolerance also. Lower soil resistivity also from 3 different models, add up together and divide by 3. And the depth also, with including tolerance. Okay, add up together and divide by 3. So the number you will get as the average of upper soil resistivity, lower soil resistivity, upper layer thickness or height, and the tolerance, including we will use for the final model. Okay, that's what I asked you to do. So yeah, that was your homework basically. And I repeated it in our last class. And I asked
Yeah, that was
yesterday.
what I needed to know. I didn't know where the process button was. Thank you.
Okay, do it fast and let me know if you're ready. We'll move forward with those data, whatever data you have. Okay, so are you done? May I start?
Yeah, go ahead.
Okay, sounds good. Sounds good. So yeah. So here, so these three models, NSEW and NASW, we used in order to get the soil model for different soil resistivity data. Now we will deactivate all those three. Don't delete it because maybe you will need it later on, but for now deactivate, but activate this ground system, which is the initial system you created. Okay, so all those three is deactivated. See the dotted line? You should have this dotted line and this ash color ground grid, but this green one or this one is the active one will be now. So you click on this ground grid, okay, and go there. See the button soil data interpretation, click on there. Now what you'll do, instead of winner method, you will click on this user specified multi-layer soil model, this one. Everyone select this one, user specified multi-layer soil model, and then edit process. So this one you will get, okay, this one you will get, and in here, see this row 1, this is the top layer soil resistivity, this row 2 is the bottom layer soil resistivity, and this is the height or thickness of the top layer soil resistivity. So in this windows, so all this area should be filled up with the data you just got by averaging your three different models. Okay, you have average topsoil resistivity, top layer resistivity, you put that here. You have average bottom layer resistivity, put it here. So these 10 don't change, but height, put the average height, whatever you have. So far, everyone should have those three values: average top layer soil resistivity, bottom layer soil resistivity, and the height of the top layer or thickness of the top layer. Put it in this. Where do we put the tolerance? Tolerance don't put for now. Keep it. Okay. So tolerance, you keep it. So using the average value, we'll start and we'll see if everything is fine. If not, then we'll use tolerance and change this number within the range of the tolerance, this, that, and that. Okay, for now, keep it as is. All right, so you put this data and click on accept. Click on accept, and close it. Okay, so now your model, physical model, is definitely with the fence and ground conductor and ground rod, everything is there, and the model, two-layer model data you put by averaging three different model, still they are there. So now what we'll have to do, we have to start our analyzing. Okay, we have to start analyzing our model, and how we will do that, that will be the part of our discussion now. So you click on analysis here, you can see. Can you see analysis here? My cursor, and here analysis. Yeah. Click on the analysis, everyone. And it will ask you save changes to grounding system geometric modeling. You click on yes, because you made a change, right? Before here was different soil model. Now you manually put the data you got by averaging from the 3 different models. So you saved it. That's fine. Now what you'll do, you'll click on the run button here. See, you'll see the run button. Click on this run button. When you click on that run button, you will have this this window here. Everyone should have this window. Frequency 60 Hertz. Solution time it's same. Just if you have it, it means your model is fine. Everything is working good. So does everyone have it? Ranbir, you have it? This one? Everyone? Yeah, is there anyone who doesn't have it? You need this one. You don't have to copy and paste it. You have it. Okay, it means your model is fine. It is working good. Close it now. Okay, close it now. So your software already ran. Okay, your software already ran, so you can close it. Now you will click on the report button here. See, report, click on there. If you click on there, some new button will pop up. Okay, new button will pop up. You have it? Does everyone have it? Okay. So when you have it, click on your grounding system here again. If you click on grounding system, you will have this window pop up now. See, the information you're having from this window is there's a 5 kiloampere of short circuit current is injected into your grounding grid. Here is your grounding grid, grounding system. And from this grounding system, the total current is spreading into the surrounding soil. Okay, and that current will pass through the soil to its source. So this figure you need. So you copy it and paste it somewhere where you are storing all of your figures. Okay, do it, everyone. So this shows you how much short circuit current you are using. Okay, so save it, and when you are done, just close it. Okay, so when you have it, now click on this grounding report. See here, grounding report. It says grounding report. Select this one, grounding report. Okay, everyone please select it, and then click on this grounding system again. This one, this main grounding system. So now we will be working only with this system. So click on this system, and you will have this system. You can maximize it. So you will have all those information here. Okay, information corresponding this knob. We have to use them. Okay, so what is important for us? First of all, important thing is ground resistance. The system you created using ground conductor, fence and ground rod, and inputting the soil data. Okay, so I'll do it again. I'll do it again. Yeah, so I am closing it. So here we are. So here we are. So what I am doing here is I am clicking on this grounding report. Before I was here, now check this button, grounding report. Rachel, did you click on this grounding report button? Everyone, click on that button. And then click on your grounding system, this system. And you will have these new windows. From here you can you can maximize. That's how I got here. So Rachel, you are asking me to do it again. I did it again. Are you there now? Okay, sounds good. Everyone, you should be here. Okay, sounds good. Now see, many things we have: grounding resistance, resistive layer effect, allowable touch and step voltage, equipotential and safety assessment, everything we have. So all of those things we'll analyze now. This is the part of our analysis. So first of all, the grounding system you created, you designed, and the data, soil data you put, according to those information, this grounding system, when I use grounding system, will give you the ground resistance. Okay, ground resistance, which we discussed in today's lab using follow potential method. So click on this ground resistance, and here is your window you'll have. Okay, click on there. And
How did you set the current to 5,000? I missed that one, I think.
Oh, this is at the very beginning we started. When we started to model the grounding system, at that point, so your current is different? Your current is different. How much? 10 kiloamperes?
No, it's like 500 amps, it looks like.
So there should be 5 kiloamperes. See, these things you should have done earlier. So go to here by clicking these tiles. See, clicking these tiles, go here and click on the source. But in order to change anything, you have to go to the edit mode. See here, edit. Yeah, Christopher is right. So you go to edit mode, and
yeah, I have 5 kiloamps there on the source.
Okay, if you have it, then you should have there 5 kiloamperes. There shouldn't be any other thing. Okay. So yeah, let's start. Let us go to the report again. We have to run it again because close it and report. After that, we can go to report and grounding report. Here we are. So ground resistance, here is the ground resistance. So this information you have to include in your report. Now see what is happening here. The ground resistance for my model is 1.0515 ohms. So how about your ground resistance? How much ground resistance you are having? Everyone. Is there anyone having more than one? Yeah, Rachel is having, Henley 2, more than one. So as a result, this voltage you are having here, see, See voltage, my voltage 5257.44 volt. So Ilya, your voltage will be less, but my voltage is high. So this is basically GPR or ground potential rise, this, and this number should be maximum 5 kV. Okay, 5 kV and less. If it is more than 5 kV, you have to modify something within your model. Okay, so whoever is having high ground resistance, that resistance you are multiplying with this 5 kiloampere of current. See 5 kiloampere of current, that is the voltage. This ground potential rise, and it is too high. Rupinder, yes, your ground potential rise is very, very high. So whoever is having high ground ground potential rise, you have to go back to your model. Go back to your model. So you can close this one. So you go to edit mode and click on your main grounding system here. So see, user specified, go back there. Now here you will use your tolerance. Okay, so you'll change your resistivity. So in here, instead of that number, definitely the one you saved, you have to include it. So initial information you have to include there in the report. But now you're analyzing, you saw that using this data, your GPR is high. It is exceeding the tolerable or acceptable level. So you have to do something. So now you will use your tolerance. So tolerance has plus and minus sign. You can increase it, you can decrease it, up to you. It is your freedom. As a designer, you will use those tolerance value and change this number. Change this number and repeat the process again. Okay, you change this number here and repeat the process again. And okay, you will go back. You will go back to your analysis. All right, run it fast, and you'll go to report. Okay, you will have it, and you'll click on here. Yeah, you have to run it, and in report mode, it's a grounding report. Okay, in grounding report, you click on your grounding system, and you will have here, so grounding resistance. So there, when you change something, you will have different value. So you have to play around and make sure that this number is less than 5 kV. Okay. So this thing you have to do. When this first thing you are done, you are fine. You have to copy this one and save it. You have to include it in your report. Okay, this is the ground resistance and GPR you got. Then the next is ground layer effect here. This one you will get. So here in you, so here I am having 3000. How much you are having, Joshua? So this number, if other than 3000, you have to change it. You have to put 3000 because on our surface level we are using crushed rock, and crushed rock is having, this is the resistivity of the not top layer soil, but extra layer what we are putting. It could be asphalt or crushed rock. So this is the resistivity of the added surface materials, which is crushed rock. It should be 3000. Everyone change it into 3000, and the thickness should be around 6 inch or 15 centimeter. So crushed rock thickness should be 15 centimeter. These two number you have to change. Okay. So yeah, resistivity layer effect. That's right. That's right. So these two number you have to change, and you have to copy it and save it. All right. So here, when you are done, you just close it. Then the next button, allowable touch and step voltage. So depending 3000, yes, 3000, change to 3000. That's right. 3000, and the thickness should be 0.15 meter. Okay, now you have your model. It is more or less reasonable. It will be reasonable when your GPR is less than 5 kb. All right. Now you will click on their allowable touch and step voltage. You click on there, you will have this window on your screen. Okay, in this window, so the body weight 50 kilogram, it could be 70 kilogram. If 70 kilogram, this number, this is the allowable, permissible or allowable touch voltage is that much. Okay, permissible or allowable step voltage is that much. Here is the allowable voltage, touch voltage and step voltage. All right, see one thing, over native soil. So over native soil, allowable touch voltage is only 370 volt. It means if you remove your top extra layer of crushed rock, then that will be the allowable voltage level. It is very low. Okay, so it means for a very low voltage, you will have you will be electrocuted and it is not safe. So you have to have higher allowable touch voltage and step voltage. That will be safe for you. Okay, so this one also you have to copy and save and include in your report. All right, so when you done that, close it. And now we'll look at the equipotential here, equipotential and shape assessment, this one. When you click on that, you will have a new this button, new button. You update it, click on the update. See, you will have this equipotential line surrounding your grounding. You see, it is the software is calculating it. So here, see a boundary. You have to make a, you have to set up a boundary surrounding your substation. So the calculation will be limited within this boundary. Okay, now according to my model, okay, and see from here, earth voltage profile. So this the earth voltage according to the this color. So the line with this color, equipotential line, definitely will have 3.7 kV, and this red color will have 5 kV, around 5 kV, and red line is this one. They are will be 5 kV. So see, my model is not done. I didn't put any conductor here, but your model is complete. You will have different number depending on the design. So this is the earth voltage plot. Okay, so that is the voltage gradient you will have surrounding your substations. All right, so now this one you can have a look differently. You could click on this one, then so this will be the 3D view of your grounding grid. So this is grounding grid, this is my conductors fans, and this represent the potential. So where the spike of the potential you can see from here. Okay, so this thing you can have, and you can close it and go back there. So this also you have to copy and paste, keep it. Is rate too much potential? So yeah, 5, yeah, maximum potential is 5. But this is showing you where you having how much potential. Okay, this earth voltage, because see the green circle here. So 5 kiloampere current, if it is injected here, then this will be the gradient of the voltage surrounding my substations. Okay, you have to have it. Now the main thing is touch and step voltage. So you click on this touch one. Okay, so select this one and update, then it will calculate your touch voltage. It takes a little bit of time because a lot of calculation. Yes, we have the touch voltage profile, and I know the allowable touch voltage for my grounding grid, right? And you also know yours one because you already found it previously. Now the allowable touch voltage is 1420.4 volt. So this number is the same as when touch voltage was shown, the permissible touch voltage that is given here. And according to this analysis, touch voltage analysis, the maximum touch voltage is 1.7 kV. 1.7 kV. Okay. Now the thing is, we have to use the definition of touch voltage and we have to measure it. Okay, we have to measure it. How we'll do that? We will see, these are fans, right? These are fans. You also is having your fans. So from fans 1 meter away, any point will have the voltage. That voltage is your touch voltage. Okay, so in the fans, within the fans also will have different voltage, but touch voltage you have to measure 1 meter away from your fans, outside and inside. So what you will do is your model, outside of your model, you will find 10 points in the corner and close to the gate. Okay, in different areas you will find 10 points which are 1 meter away from the fence, outside. The same way 10 points inside the substations, inside the fence, 1 meter away inside and 1 meter away outside. So this is your choice. You can choose whichever point you want, but corner definitely you will choose. Corner and other point together, 10 points outside and 10 points inside, 1 meter away. Okay, so you can see here, see this one. This one is not active layer. That one is with I think, I don't know which this one is with. So don't change. It says active layer is.
Hey, Nurul.
Yeah. Go ahead.
So for yours, it says Equitouch voltage plot with respect to main grid at the top right there.
Yeah.
Mine just says it doesn't say with respect to main grid. Is that a problem?
So what does it say?
It just says Equitouch voltage plot. It
Oh,
doesn't
that's
say
okay.
with respect.
So is there anyone who is having the same information without this with respect to main grid? Or oh, that's not a big deal. That's not a big deal. This would be okay. No, that's okay. Main thing you are having your. So here, yeah, Hanley is asking 70 kb or 50 kb. Up to you. You can use 50 kb or 70 kb, because whatever you will use, I will be able to see whatever you were using, and according to the body weight, allowable or permissible touch and step voltage will be different. Okay, so use 50 kb, 50 kg or 70 kg. Okay. So, and whatever equipotential line we're having in earth voltage and touch voltage, this is depend on the soil resistivity, and if you change the grounding grid, also you will have different voltage profile. So the thing is, you have to measure the touch voltage 1 meter away from your fence. Okay, I have here 1 meter, but I cannot. There is something it is related to. Maybe let me check it. Maybe this one is, it is not. So oh, this ground rod, red one is ground rod. I will activate the ground rod. Oh, ground rod, yeah, ground rod. So say 1 meter. All of you have this scale already, because you are putting the counterpoise. So from your fence 1 meter away, okay, in the corner and some other places. So now I'll show you how we will know what is the touch voltage basically. So let's say this is your fence line. So from here 1 meter away. So whenever you moving your cursor, look at here, the touch voltage is showing here. It is changing. Everyone, please pay attention, because this is important. You have to use this number in order to record it. So see, within the boundary, whenever I am moving my cursor, this number here, touch voltage is changing. So here you will put your cursor 1 meter away from the fence, and you'll see in my case it is 278.5 volt. So this is our touch voltage here. Now you move this distance, and you move somewhere else, your voltage will be different. So this is the 10 different point you have to select surrounding your substations, and the number you will get from here, the number you will get from there, that will be the touch voltage, and that will you have to include in your report. Okay, so outside of the fence and inside of the fence, okay, you have to do that. You have to do that and be very, very precise. So don't make the distance more than 1 meter. Okay, so in each case you will show this figure as well. Okay, here you see. So here is my grounding grid, and here is the touch voltage profile. So touch voltage is higher surrounding the fence. Okay, somewhere this is spike. Okay, but I can calculate it using the software. Okay, so you can rotate it as in AutoCAD. So this figure also you will save and you'll include in your report. All right, so definitely this one you will include, and in some points you will show me that you put your cursor 1 meter away, so that I can see that you are putting your cursor 1 meter away, and this number also will get saved. So total you have to save, okay, including this information, including this information. You can just you know take a print screen and then even include it. So this is about touch voltage. Any question about touch voltage, how you will have to figure out it? My interference is within the lowest potential. That's good. That's good. So my photo is not important, Eric. My photo is not important, but you have to include some photos. Okay, how measurement is done. Okay. So not necessarily there will be my photo, and don't put my photo. That will be better. Oh, your photo, it won't make any sense if you include your photo, because you didn't do anything. Anyways, if you like, if you would like, you can include your photo. Okay, that's fine. But mainly photo we include when we are taking the data, doing the experiment. That photo. So include some photo from lab 1, lab 2, lab 3. Yeah, that will be good. And this is very important. Okay. So do you have any question about touch voltage? Anyone? So yeah, Eric, your photo when you are measuring touch voltage? I don't think that you measure touch voltage. But using the software, you don't have to include anything extra photo, except model will give you the images. That is good enough. Okay, again, any question related to the touch voltage? And you'll see the touch voltage will be below the permissible touch voltage that you will have. Now, if any certain point your touch voltage will be higher than the permissible touch voltage, then again you have to redo your design. You may have to include more conductor. The distance of conductor, instead of 10 meters, maybe you have to make it 8 meters. Okay, maybe you have to include more ground rod. Okay, so that's what is done in a real life situation. If you and whatever you are doing here, that's the report, and according to this report, the real grounding grid will be constructed. Okay, so that's the way you have to
So I think most of us don't have it making the report with respect to the main ground, so we don't have that margin. Do you know how you got that to do an auto comparison?
So do you have this information, V voltage, permissible voltage?
Yes, but without the margin there.
Or this margin?
Yeah.
Minus 17.43. Yeah, margin is okay, but this is a threshold. Okay, so margin you have minus 17.43%. That will give you more safety, But if your design is good enough, then your calculated touch voltage will be below the permissible touch voltage, including this margin. Okay, so you just analyze it later on, and you will see that's what will happen. And if you will have any hardship, in case your touch voltage is higher than this number, then definitely you have to redesign. Redesign doesn't mean that you have to throw out everything what you did. You just have to modify something. You have to put the conductor closer. Okay, and on the other hand, you can change the soil resistivity within the tolerance. So different way you have to act in order to achieve the touch and step voltage, which must be less than the permissible, or at least could be equal to the permissible, also is acceptable. Okay, so that's how we'll do. Now next step is step voltage. You select it and update. That's what we'll have. Now definitely step voltage is the voltage difference between 2 points which are 1 meter away from each other. So what you'll do is you don't have to take 20 step voltage values. You will take 10. So 5 outside of the station and 5 inside the station. So definitely you'll take the reading close to the gate, because that's the area where the possibility of the personnel to walk is the highest. Okay, so in my design, here is the gate. So you will take 1 meter, 1 meter. Okay, 1 meter, and I'll show you what you'll do. So you'll put this 1 meter distance in 5. You'll find 5 point outside of the fence. So see how we'll measure. So if you put your cursor here, the voltage shows 36.07 volt, and in here it shows 36.33 volt. So voltage difference is not that much. So step voltage is definitely the voltage difference between these 2 points, which is 1 meter away from each other. So here 36, here 36. So step voltage is here almost 0. Okay. Now if I'll put it here, this I'll put it here. Instead I'll put this way. Because here the line you are seeing, this line is equipotential line. So voltage in any point of this line is the same, 83.82, and here. Yeah. So within this line, voltage is the same. Now the way I put the scale here, voltage is 70.5 volt, here 57.5 volt. So difference, what will be the difference? That will be the step voltage here. Okay, so step voltage usually is not that high. Touch voltage is sometimes could get higher than the allowable, but step voltage most of the time they're much below than the permissible or tolerable level. Okay, so step voltage, you have to put your cursor in 2 point 1 meter away from each other, and the difference between these 2 voltages is the step voltage. So again, 5 reading outside of the fence, 5 readings inside the station. Inside the station, yeah, you'll choose wherever you want. Okay, and this data you have to include in your report, final report. Again, for this also you will go there and you will find this one. Okay, and one figure like this also you have to include, and even you can no, this is not that, this one will give you. So highest step voltage you are having is 308.2 volt. Okay, maximum voltage, and your threshold is that much, it says here. Okay, so Yeah, this also you can copy and paste and include in your report for step voltage and for touch voltage as well. So software is very user friendly. You just have to take your time and go through this. And the way I discussed, I think you got the point. If you have any questions, just go ahead and ask me. I'll repeat it. Is there such thing as a graduate line? What do you mean by graduate line? Yeah, we use term equipotential line. Graduated line, no, I didn't encounter this term. Like yeah, could be there, yeah, could be. And so this software is modifying each year. Before it wasn't there, but now maybe. So if you have times, just go through the instruction, and instruction you can get the software instruction you can get in help here. See, help topic, you could get to the help topic there. Yeah, so basically you can go to the help and you can search for it. Maybe they included it there, I don't know, but before it wasn't there. Okay, so maybe nowadays they included it. All right, so yeah, any question related to the step voltage? Yeah, so yeah, you can search for it. Okay, so if you don't have any question, then we are done with all the labs and the modeling also, and this touch and step voltage, if you compare with the measured touch and step voltage, there is a huge difference. But in real project, they are very close. They are almost the same. Okay, so this is the way you have to analyze. But if you see that your ground potential rise is more than 5 kV, and touch and step voltages or potentials are beyond the allowable level, definitely you have to modify. You have to modify your model, and you will modify just first try to not change this grounding conduct or anything, just modify the soil resistivity, okay, top and bottom layer and thickness within the tolerance you will have. If that helps, that's good. If not, then you will start to change the hardware hardware installation. But you have to make sure that your result is within the acceptable level. All right, and when you are done everything, you'll put a final conclusion. So in lab report, sample report, you could see the conclusion at the very beginning. So I'll ask you to include the conclusion at the end. Okay, so final conclusion should be at the end. And when you will prepare a report, follow the rubric. Two things you have to follow. First, the lab report, sample report. Only thing you have to do differently is the final conclusion you will put at the end of the report. Okay, and the rubric step by step, whichever you have to include, everything is there. You have to follow that, and for which part how much mark also is given there. That will give you a very clear idea how you have to organize your report. Okay, any question? Any other question? Okay, if you don't have any question, then so whatever is discussed, it is basically related to the final lab, which is lab number 4. So in lab number 4, definitely we will be there If you have any question, I will just answer those questions. But if you are fine, you don't have any question, you don't have to be there. That is fine. Okay, because whatever is related to lab number 4 is already slowly discussed in all 3 labs. Okay, that's all about the designing. So if you're fine, that you're fine, you don't have to be there. But I will be there. If you have any question, I will answer it. Okay, but my suggestion would be you just start to prepare a report, right? Right, because you know everything and you have all the information. So analyze, make analysis, save all the images, and just start to write the report. A report should be professional. Okay, should be professional. So any question? So if you don't have any question, then